Okay, welcome everyone. This is Eclipse OMR, a modern open source toolkit for building language runtimes. My name is Daryl Maier. I'm from the IBM Runtimes group at IBM Canada. I've been doing compiler development for about 20 years now in my career at IBM. Some fairly propeller head stuff, I think. Been working on HPC. The last 15 years I've been working on a dynamic compiler for Java, so as part of the J9 Java virtual machine. Recently we spent about 3 years taking a lot of that technology and open sourcing it. And these days I'm working on trying to get that technology used outside of Java and into other sort of language environments. And we'll be talking a bit about that today. First of all, the standard, because I work for IBM, I have to have some disclaimers that they can disavow anything that I say. So today, what I'd like to do is to take you through the Eclipse OMR project, what it's about, what its goals are, what its origins are, and where it's really going. I'd like to show you what's been contributed so far, and some of the technologies that are already out there that are consuming it. And what are some of the future directions of where this is going, and perhaps most importantly, where and how you guys can get involved. So I'm going to cut right to the chase and just say that the Eclipse OMR project was created about a year ago in March. It just had its first birthday. And what Eclipse OMR really is an open source project that provides language agnostic parts that you can use to integrate into language runtime. So you can use these things to supplement your runtime. So for example, it would provide technology like GC technology or compiler technology or threading technology, that sort of thing. We have a logo, we have a color scheme, so it's got to be an official project. The code is all available on GitHub. We try to make it as consumable as possible in different environments, so it's got a dual license, so EPL v1 and Apache 2.0. And contributions are very much encouraged, and like as many people as possible to get involved with that if you're interested. So before anyone asks, and perhaps the most common question we get is what OMR actually stands for. It actually doesn't stand for anything because it's not an acronym. When we started this work about 5 years ago, the intention was to call up the Open Managed Runtime, but as it turns out, as this technology is actually, as we got into this project, it turned out that it's actually not a managed runtime. It's actually different than that. It's really just a collection of components that you integrate. But over that time, the acronym kind of persisted throughout the code base and in people's vocabulary, and it's really hard to change that. And coming up with another name is very, very difficult, so it's stuck. And then the other most common question we get is, what does this have to do with the Eclipse IDE? And the answer is nothing, because it's really just a project of the Eclipse Foundation, and it has no association at all with the Eclipse IDE. So a bit of background on where this came from and why it's come to be. So when we talk about language runtimes, we really want to understand sort of what the different parts are that make up a typical language runtime. And if we focus on something like Java, for example, and a typical Java execution environment, it really looks something like this with all the from a very high level. If you look at all the pieces. From a developer point of view, you typically start with the Java source, and it gets compiled down with Java C into some sort of bytecode representation. And then that bytecode representation is executed on a bytecode interpreter that follows the Java VM specification. As part of doing that, Java does have a memory model. It does make requirements about the lifetime of objects and managed memory and that sort of thing. So Java typically has some sort of garbage collection technology built into it as well. Java is also a write once, run anywhere technology. So in order to handle that, you have to have, or you would usually expect to find some sort of a abstraction layer that sits between your virtual machine and then the underlying operating system or the underlying hardware that it's running on. And then, most modern JVMs these days do require some kind of compilation technology to translate bytecodes directly into some sort of native instructions in an optimal way and then execute that. You pretty much have to have that in order to get any sort of decent performance these days out of Java. And also, things don't always go right, so you tend to require some kind of diagnostic and tooling hooks into your runtime to be able to help you debug your application, or in the worst case, if there's something wrong with your VM, you need some technology there to help you out. So, if you look at Ruby now instead of Java, and you're doing this from a very high level as well, you're going to start to see a lot of the same kind of components here. So, even though things are implemented a lot differently, the components look more or less the same. So you do start with a Ruby source. It gets translated down to some sort of Ruby instructions that get executed in some kind of a bytecode loop within Ruby. It does have the notion of managed memory and object lifetimes and that sort of thing. So you do need some kind of garbage collection technology to take care of that for you. It does run on multiple platforms as well, so you need some way of abstracting what your VM is doing from running it on the different targets that you care about. And again, you may have you would expect to find some diagnostic capabilities built on top of that as well. JITs are not necessarily a requirement for Ruby. There's certainly some schools of thought that think that compiled code is where you're going to get a lot of performance. We're actually one of those schools, or IBM is one of those schools. But what you would find in some Ruby implementations these days is not a JIT compiler, so it's a bit optional. So that was Ruby. A lot of similar things with Java, and you can do the same kind of argument with JavaScript as well. You're going to see a lot of the same kind of components if you look at something like that. So even though there are a lot of similarities between these different language environments, what you tend to find is that because each of these language environments has been developed completely independent of one another, they're going to have very different implementations for all those different components. So what that really means is that if you're going to make a significant contribution to the compiler technology that underpins Java, and you're adding some cool RDMA support, or you're adding some SIMD support, or GPU support, something like that, that effort that you took to put into Java is not going to carry over into any of these other languages or language environments. You're going to have to go through the effort of re-implementing this for Python or Lua or Ruby or something like that. You're going to have to walk around to all those different languages and do the same thing, which isn't a great way of proceeding. So the point being that any investment that you make in one of these runtimes isn't necessarily going to carry over to any of the other ones. And this is particularly important as we start to move things onto the cloud. So a lot of these languages underpin the cloud, and this is particularly important there. And the reason is that cloud platforms are really built on runtimes. So a lot of the applications that are running the cloud, that are making the cloud what it really is, are built on different language environments. So all the things that make a cloud, the resiliency, the security, the efficiency, the elasticity, consistency, all those things are there because of the applications that have been implemented there. And what that means is that the way that clouds can actually grow is by their underlying languages. So, the more kind of features you can get into those languages that build the cloud, the better off you're going to be, and the way that the clouds can actually advance. So having a lot of different language environments that each grow at different rates is really going to hurt the development of the cloud. So it's something that would be great to be addressed. And that's where the Eclipse OMR project kind of came into being. So the mission of the Eclipse OMR project is really to build an open, reusable language runtime foundation for the cloud. And it's got a number of tenets toward that. The first is really to really really address those issues of having different components across all these things, but by really having sort of a common place where you can go and invest in this kind of technology, and you do all your work in one place, and it can sort of naturally be consumed by all these different environments. So it's really sort of a place where you can go and innovate, and then they can be picked up by different components. So it's going to help accelerate cloud platform development. The other thing is that it's going to be done in full cooperation with the language communities that are out there. So a lot of the languages that we talk about, they've been around for a while, and they have some fairly well-established communities built around them. They have their own processes, they have their own way of working, they have their own extensions, things like that they built into their environments. And the intention of this is not to be very disruptive in all those environments. It's really to work with those communities in order to get this kind of technology integrated. And the other thing is that there are a lot of different, like where you find a lot of innovation in language runtimes comes from a variety of different places. These are like corporate developers, these are researchers in universities and colleges, there's students, there's guys in basements that are working on hobby projects that all have great ideas that they want to contribute, but what they tend to do is to sort of focus on one of their pet languages and put the technology in there. So what this would enable them to do is to really contribute at a very common place, and and get that investment deployed more broadly. So, I mean, that's a great idea, but it would require a fair bit of capital to get going on that, right? You really need to have all these different runtime pieces in place in order to really start to make this happen. So where would all those pieces come from? Are we starting from scratch, or what are we going to do? Well, when IBM thought about this a few years ago, what we had at that time was a very mature, very stable, very high-performing runtime system for Java. And we decided to start there and see if we could look at that and understand if whether or not there's parts of that we can actually make specific to Java, but there's also parts that we can make language agnostic as well. So we weren't quite sure how much we could do in either direction, but we did take a look at it. So again, standing back and looking at the high level of the runtime system, you tend to see all these different components, similar to what we saw before. But when we did start going through each of these things, we did figure out there's actually quite a bit of the code that you can actually isolate into a language agnostic bit and then push all the Java bits down into their own kind of glue layer. So what we decided to do was to go around to all these different parts that make up a runtime system and then start to do that separation. And the language agnostic bits really did become the basis of what was contributed to the Eclipse OMR project to start with. So now, as part of this project, it does have a number of sort of goals. So the first is that it doesn't have any of the components in this toolkit does not have any language semantics. So it doesn't favor one implementation or one language environment or another. So for example, it doesn't favor Java. It doesn't force if you're writing something in Lua, it doesn't force you to have to obey Java language semantics in order to implement something for Lua. So the intention is to make this as clean as possible. It's also not a language runtime, which is what I've said before. It's very much a toolkit that for a particular language or for a particular environment, for your particular needs, you go around and you sort of pick and choose the parts that you want. If you just want the garbage collection technology, you can just go out and take that and assemble that into your runtime if you don't care about JIT technology, for example. And the other thing is that it should actually be fairly easy to integrate this technology into any language runtime. And this could be a new toy language that you're working on. It could be something that's been out there for 30 years or so. That's really the goal there. And the other thing is about it doesn't actually influence the language semantics, right? So I talked earlier about the working with the communities. The intention here is not to cause a lot of these language communities to change their code to adapt to this technology. It should really be the other way around. This technology should be flexible enough to sort of bend to the needs of those particular environments. So that's what we did. So we did actually go about and take all those different components. We isolated the language agnostic bits of it. We created an Eclipse OMR project, pushed it out the door. Like I said, it's been out there for about a month, for about a year now. The rate of contributions has actually been fairly healthy. It's doing quite well. I would say that on average we're getting about 5 to 10 commits a day, and so it's really only sort of taking off from here, so that's great to see. So just looking a little bit under the covers into what has been contributed so far. So it's a fairly diverse set of technologies that you can use to integrate into different runtimes. So I talked before about the platform abstraction layer. So we do have technology for isolating, for building that abstraction between your runtime and the underlying operating system or architecture. So that's like the port layer, the thread layer, some VM technologies as well. There's a world-class garbage collection technology that's been out there. Same thing for compiler technology as well. There's something called JITBuilder, which is a simplified interface to enabling the compiler technology in a particular runtime. There are components to help you get information out of your runtime and into some sort of a format where you can actually attach tools and things like that to it for doing diagnostic work. And there's sort of a unit testing framework that's being developed as well that allows you to test the different parts of the code that you actually want to contribute. So far to date, there's probably around 800,000 lines of code. I would say that is growing fairly steadily every so often because there's more and more technology being contributed to this all the time. I do want to drill into a little bit deeper into a couple of the technologies that we do have in the box. So these are some of the ones that different language communities are particularly interested in. So the first is some of the garbage collection technology that we have. So I said before that the origin, a lot of this was the J9 Java virtual machine, and the GC technology that was developed there has been developed for many years. It had really matured out in the field, and it really does support. It is a world-class garbage collection technology. So it does all the things that you would expect a GC to do these days. So it's very parallel. It's very scalable. Java had some very specific requirements of being able to run on very small devices like watches up to very large servers, very large clusters, things like that. So it had to scale very well. So it does that. It understands multiple cores, it understands threads, it understands NUMA topologies, things like that. So it does all those things. And it's fast too. So with that as a starting point, one of the most basic things that you can do is just sort of hook up a Mark Sweep garbage collection technology. And there's been a few projects that have done this already, and I would say that for the most part it usually requires less than 100 lines of code to make that connection, so it's a pretty good consumability story to begin with. And then depending on what your needs are, you can start adding more and more advanced GC technology to that as well. So you can add compaction, for example, if you want to reduce fragmentation in your heap. You can add a nursery if you want to add some generational capabilities. And if you want your GC to run in parallel with your application, you can, or concurrently with your application, you can add, there is support there for concurrent GC as well. So a lot of really good things there to get your GC going. Just to give you, because it is one of the central pieces of a lot of this technology, just to make sure that everybody understands what Mark Sweep GC is and what it can do. So what this really means is that periodically the application thread, the threads in your application, or the thread, if your VM doesn't support threads, will have to stop. And then you try to find out what objects are live by starting with these root sets, which are typically like global variables or statics or the thread stacks. And from there, you try to figure out what objects do you happen to see. And when you see an object, which means it's reachable, you mark it as live. And then once that's done, you have this sweep phase that basically goes through and finds anything that hasn't been marked and just sort of sweeps it away and then reclaims that memory. So, and then the threads restart and you can carry on. So fairly simple idea there. And then hooking this up to a runtime is actually fairly simple. I don't really want to show code, but I just want to sort of talk about concepts. You do require some kind of initialization. You do need to be able to describe what your objects look like and how they're laid out. You need to be able to provide some kind of functionality for allocating these objects and getting them initialized when you create them. You need to be able to poke the GC to tell it that you need to do a collection. And then, configuring your heap and tearing it down is also important as well. So, like I said, this is all part of the less than 100 lines that you may need to get this integrated. So, a good consuming story. Another thing that's in the box is the compiler technology. So this is another popular, bit of another popular component that's often integrated into different environments. So like the GC technology, its history has, like this compiler technology has been developed for many years. The interesting thing about this, though, is that it did come from, it was developed initially as a dynamic JIT, right? So it didn't actually start as a static compiler. It did start, so a lot of the things that it had to solve early on were intended to be solved in a dynamic environment, which is really good for runtimes these days. But having said that, though, over the years it has proven its flexibility by being able to run, but by being able to produce static compilers and binary retranslators and stuff like that. So it is a fairly flexible piece of technology. It is a clean room implementation, so it was developed completely from scratch without any IP from anywhere else, written in C++. And like I said, owing to its embedded heritage, its design goals were to have really fast startup time, really fast compile time. It's very strict on memory management. A lot of things are very tightly controlled, but on the other hand, it can actually be very flexible, right? So if you happen to be running on a very small device, you can configure it to use very little scratch memory, and therefore you may be hurting some of the performance you might be getting out of it. But if you're running on a very large system, you have a lot of scratch memory, you can widen that and perhaps get more performance out of it. It does have the kinds of optimizations that you would expect any modern optimizer to have. So a lot of high-level optimizations, classical stuff, loop optimizations, data flow, speculative, control flow, that kind of thing. It generates code and does deep platform exploitation for a variety of different platforms. So it does the sort of traditional x86. It does 32-bit ARM, but unlike some other systems, it does handle Power and System Z as well. So it's got a fairly wide base there. It does do dynamic recompilation, so with profile-directed feedback. So this is really where a lot of the performance out of this dynamic compiler comes from, is from that, which has been built in from the start. And it does speculative optimizations as well. So a lot of fairly advanced things that are in the box. That's good. Just looking at the block diagram of the different components here and how things flow together. The main thing that has to be contributed by a runtime, a host runtime, is, you really have to somehow get your representation of a method into a form that the compiler can actually consume. So what you typically do there is produce what's called an IL generator. You need to get the let's say your bytecode representation or your instruction representation into the IL representation of the compiler. So there's a couple of ways of doing that. You can write a native IL generator. You can write a JITBuilder. I'll talk about that in just a sec. But once you get this IL into the optimizer, it behaves just like an optimizer. You can throw many different strategies, optimization strategies at the code. I usually have a slide where I list all, I think there's 90 or more optimizations that we have, the intention being to just overwhelm you with information. But I don't have that here, but there are many optimizations that you can choose and add to any strategy that you like. It does tiered compilation. It's been doing that for almost 20 years now, and it was one of the things that we did from the start. And of course, code generation, it does that. All the while that this is operating, it's in sort of constant communication with the language environment itself to ask questions about things like what is the offset of this field in this object, or talking with a runtime profiler as well if that capability is hooked up to get that kind of information and fed into the optimization process. So there's a couple of ways, there are a couple of straightforward ways of actually hooking up this compiler technology to your runtime. The first and perhaps the most brute force way of doing it is to actually write your own native IL generator. So what you basically are responsible for is producing the IL in OMR directly from whatever bytecodes your method happens to have. You're likely, going this path, you're likely going to have the deepest exploitation of this technology possible. And you're also probably going to get the best performance by doing it this way as well. So that's one of the advantages. Of course, the real challenge here is that it can be fairly overwhelming to go this route, especially if it's sort of your first time doing this. And because the IL itself can be complex in some areas, and it's got some nuances that need to be sort of understood. And you're unfortunately, you're assuming all the ownership of the complexity of this. You're not really, you're taking it all on yourself. But there's some pretty rich rewards you can get from that. So knowing that this is sort of a steeper learning path, within about a year or so, we decided to come up with a sort of a simpler way of taking this compiler technology and integrating it with a runtime. And that's where JITBuilders come in. It's sort of an IL generator with training wheels. Really, it's really trying to simplify the process of taking the compiler technology and plugging it into a runtime. I've got a couple of links on here to some blogs that we're developing around this technology, trying to introduce it. There's some Docker images there if you want to go and start playing around with it as well. So there's some cool stuff there. But the way that it works, it's really just a simple API that you use to describe what it is that you're compiling. So in a particular runtime, you would have to describe your method, what its signature is, what parameters it takes, what types are you using, how do you actually interpret your bytecodes, and what does it actually mean to interpret those? How do you do your compilation, that sort of thing. So it's a fairly straightforward interface for describing that. And then what the end result of that is it produces the IL that can be consumed by the compiler. So the downside of doing this is that because it's a much more general framework, you are sacrificing a bit of performance in order to achieve that. And the technology is very much a work in progress. We've been taking a lot of this technology and using it to integrate it into multiple different language runtimes like Lua and Ruby and some other VMs as well. And every time we do that, we learn something new or something different that we need to add to this kind of technology. So that's where that's going. So that was a bit about what's in the box. So in terms of who's actually using this technology right now, I would say that perhaps the best ambassador of this technology right now are the IBM SDKs for Java. So these are commercial products. I've talked a lot about the IBM SDK so far, and it's really been the origin of a lot of this technology. But after we had gone through the effort of actually separating the language agnostic parts from the Java parts, we were able to ship Java 8 in 2014 with the language agnostic technology built into it. And it really exercised a lot of the extension mechanisms and the consuming mechanisms in that. So the real point of that was that it really showed that the thing that we did was actually fairly, like, the quality was there, the performance was there, and it was versatile enough to be used in that way. So it really worked out well. So. One of the next things that we're looking at is something called OpenJ9, and we've already announced that IBM will open source the J9 Java virtual machine later on this year. So that's coming. The work to do that is actually proceeding in parallel with the IBM's SDK for Java 9. So there's going to be 2 of those things arriving later on this year. Why open source OpenJ9? Well, there's a few reasons for that. First is the fact that, a lot of times when, we work with partners or customers or researchers or whomever, and, they've got some great idea and they want to get that implemented in the technology, it's actually difficult working with them in some cases because it is closed source. They can't actually do the work themselves. So, it's a more complicated arrangement getting some of the stuff, and it really inhibits some of the innovation. So getting it out in the open is important for that. Also, I personally was very much on the front line of a lot of the Java benchmarking wars of the late 2000s, and I can tell you that those wars really drove a lot of the innovation into the Java virtual machines. And so, for example, the advancements that we made in some of the GC technology and some of the compiler technology in order to drive some of those benchmarks was really good, and I think that a lot of that's going to apply here as well. If you get this open source. And another area that, what we tend to see is that, when investments are made or contributions are made in a particular platform, so for example, if I'm implementing some GPU support on a power architecture, oftentimes that kind of contribution would also apply on x86 or ARM or something like that. And you don't often get that sort of cross-platform. It doesn't actually percolate across platform. And by having the code out in the open, someone can actually take that code and actually port it to x86 or port it to ARM or wherever it happens to be. And so it's really, encouraging that. So there will be an open source project created for OpenJ9. It really is the most robust, well, it is a very robust extension of the Eclipse OMR technology. It is kind of going back to its Java roots, so it is really pulling on it in a lot of different directions, which is really good for stressing it out. The intention is that this will be the upstream repo for a lot of Java VM projects, so for example, the IBM SDK for Java. The intention is to have it as a very open, run it as an open community, encourage lots of contributions to that. It's not public yet, but the expectation is that this is going to be open around the IBM Java 9 release later on this year. There's a URL there that you can go to if you're interested in tracking the progress of that and getting information about this project as it comes along. So Ruby is another area that is consuming this technology. This was actually one of our first proof points of this technology outside of Java. It was developed very early on with some of the refactoring that we were doing. What we were able to show was that we can take the GC technology, and we've got that integrated into Ruby 2.2. We took the compiler technology. We also had it in 2.2, but it's also in Ruby 2.4. And these proof of concepts have actually really shown quite a bit of potential in terms of the quality of the code and the performance that they're able to achieve. And the other thing is, and we're talking about working with these communities, it runs the things that they care about. So for example, this code will actually run Rails, and it does it quite well. So that was really good to see. So we're kind of encouraged by this, and what we're thinking that the next step for this technology could be is to actually help achieve the Ruby 3x3 target. So if you're not familiar with what that is, so Matt's basically said that by Ruby 3, the performance of Ruby 3 should be at least 3 times the performance of the previous generation. And we think that a lot of the technology that we have here is well positioned to help achieve that 3 times performance gain. We've been doing a lot of prototyping, a lot of study of the code, and the kinds of things that we're looking at that are likely going to be needed in order to achieve that are just better communication between the runtime system and some of the technologies like the VM, JIT, GC, that sort of thing. So for example, things like when classes get, when classes die or when classes get overridden, things like that are extended in some way. You've changed things in the environment that a compiler or a GC would need to know about. There's not really a lot of that communication yet, but it needs to happen. And then, profiling, type specialization of your code, and doing a lot of inline optimizations. They're the kind of things that can really give a lot of performance in some of these environments. So we're working on that. We do want help. This is open as well, so we do have a repo there. If you're interested, I encourage you to go look at that, look at the issues in that repo and search for the help wanted tag, and by all means get involved. Lua is another area that we've kind of moved into as well. This actually started as a bit of a pet project. We just kind of wanted to see how easy it would be to hook up the compiler technology into Lua using JITBuilder. And as it turned out, it was actually relatively straightforward. So, in terms of the changes to the VM, it only needed about 50 lines of code to Pacrio Lua. And we probably had to provide about 2,000 lines of code for the actual compiler itself. So, and just by doing that, we were able to achieve some fairly respectable performance improvements on a few tests. And but we were very encouraged by that. And what that really caused us to do as well is to start looking at other ways that we can really improve performance. And so we've done some experimentation with more advanced compiler techniques, similar to what we were doing with Ruby, like with the type specialization and the inlining and that sort of thing. And the kinds of performance that we're getting there now is kind of approaching LuaJIT performance in some cases. So we're very encouraged by that, and we really want to accelerate that kind of work and to get that integrated, because we think that there's quite a bit of potential here. There is a repo for this. Again, we want help for that as well, so by all means, help out. There's also a talk I've got listed here that one of my colleagues gave at FOSDEM a few weeks ago. So he goes into more detail as to the work that we've done with Lua so far. SOM, don't want to keep going on this, but I have to mention SOM because a lot of these different sort of language frameworks that have come out all seem to have an implementation on SOM. We've done that as well. It was one of our early proof points. It didn't take much effort, like probably a week, maybe 2 weeks, and you get fairly decent performance out of the benchmarks that they have there. So it is certainly possible to integrate with that too. And the last thing I want to mention is something called Base 9, which I don't think most people have heard about yet. So what this is it's sort of an educational VM that we're developing that will be used to demonstrate how to integrate some of this technology with a typical language VM. So it's really a training aid for teaching how you can take all these different components and integrate it. It's fairly simple. At the moment, it's got a very small bytecode set. It's stack-based. It has a limited set of types at this point, but it certainly is extendable. We've done some tutorials. There's some educational training on how to integrate the compiler technology with this. Performance-wise, it behaves phenomenally. So like there's an example there about getting 760 times performance improvement by over the interpreter on some basic fib work. It certainly is possible to integrate GC technology here. We need to add like an object model. We need to add some array allocations. We need to add some other things like that. But then, we'll have something in place where we can demonstrate GC hookup as well, and then on with tooling as well. So there is a repo there as well that you can go check out. Okay, so looking forward where this is going. So this is by nowhere near the it's just the beginning of this technology. IBM itself is still very actively contributing to the technology. Not everything that we wanted to open source did get open sourced. We're still working on a lot of cool stuff. Like for example, in terms of the garbage collection technology, we're working on releasing our region-based garbage collection technology for doing that kind of allocation. Compiler technology, there's still a lot more dynamic compiler technology that we need to sort of separate from Java and then push out the door. So things like more speculative optimizations and the runtime assumptions and class hierarchy work and things like that. So there should be more of that coming over the next little while. Just to sort of show the quality of this code, IBM is actually pulling this in every hour, all the commits that are happening every hour, and consuming it in internal builds of some of these language products. Like any new project, we need to work on the onboarding experience. So we need more documentation, we need more designs, that kind of thing. To facilitate some of the communication that's been happening, we do want to create a discourse instance for the project so that developers can discuss in sort of a Q&A type way. So we're going to get that going as well. And we need to work on the testability aspects of it as well, right? So right now it uses Travis CI for doing testing, which is great if you just want to test on x86. But the technologies that this covers, it covers ARM, it covers Power, it covers Z. You can't really find those externally very, very easily. So there are places where you can, but it's not really reachable at this point from Travis CI. So we really need to work on extending the testing that actually happens on PRs to get those technologies rolled in. We are working with various language communities. We're working with Ruby. We're working with Lua, that kind of thing. So we need to start, showing that this technology actually does have some legs and is really going to benefit them. And then research communities, so colleges and universities. We've got a number of projects ongoing already with some universities around this technology, and that should only continue. Perhaps most importantly, how you can get involved. If you just want to go grab, fork the repo and start playing around with it, that's terrific. If you want to go the step further and actually start contributing to the code, you do need to get an account on eclipse.org, and you need to sign the Eclipse ECA because it is an Eclipse project. And then, read through the contribution guidelines, and, you should be all set, and you should be all set for your first contribution. The Eclipse Foundation has also been chosen as a mentoring organization for the Google Summer of Code. So if you're a student and you're interested, you can certainly, we have a number of suggestions of projects that could be worked on. I've got the condensed link there, so you can go check out some of those. And if you're interested, you can start writing up a proposal for one of those. We do have a number of mentors in place already for that. The window is now open for actually making your proposal submissions. So if you're interested, go right ahead and do that. If you wanted to see a little bit more about this technology in action, my colleague Bjorn Vardal has a talk tomorrow in a Tools in Action session where he's going to sort of be demonstrating how you can take some of the tooling interfaces of Eclipse OMR and plug it into an existing runtime to help solve some of the debuggability issues with that. So tomorrow afternoon, go check that out. Finally, just some contact information. I'm certainly willing to take any questions that you have, now or later. We've got the two project co-leads are listed there, Mark and Charlie. So by all means, reach out to any of us if you have any questions about this or want to get involved or whatever. And then finally, and hopefully not the reason that you're here, the booth information from IBM. For the scavenger hunt. So that's it. Any questions about the technology?
I have one question. So there are clear similarities between OMR and LLVM on some level. So what's the relationship? How do you position Eclipse OMR against LLVM?
Well, so the question was how the differences between this technology and an LLVM. So, from the roots of so if we're just looking at the compiler technology, so LLVM, this technology is more than just compiler technology, right? It encompasses a number of different pieces for runtime, but just focusing specifically on the compiler technology, it was developed from scratch, really, to be used in just-in-time compilers. So it really does solve a lot of those problems up front and sort of gets it for free. LLVM, as I understand it, and I'm not deeply familiar with LLVM, but LLVM, does have a more of a static compiler route. So it may take longer to compile things. It may be heavier on memory footprint, things like that. Whereas a lot of the stuff that we've done here really solves that out of the gate. So you know, you know, they solve problems differently, but, you know, we think that this is more suitable for language environments, like dynamic language environments. Any other questions? Okay, thank you.